In this part of the video, we are going to derive the approximations of the lateral directional mode of motion. We start by the Sphero mode, and the Sphero mode is characterized by changes in bank angle phi and the heading angle psi. The side slip angle is actually remains close to zero. However, we cannot neglect the side slip angle in the spiral approximation because all of the aerodynamic moments are dependent on the side slip. If we can go back to this slide where we see the full lateral directional equation of motion here, we see that the main variables in this motion is the side slip angle, the roll rate, yaw rate, as well as the bank angle. And to approximate the spiral motion, we have to drop some of these terms. In the textbook example of approximation, it has stated that although the side slip angle is small, we still do not want to drop this term, so we keep the side slip angle beta. And the fact that the aerodynamic contributions due to side slip and the yaw rate are actually on the same order of magnitude, then that would mean that we would keep these two parameters to approximate the spiral mode. This means that we're going to drop the roll rate and the roll angle for our spiral approximation, although we know the fact that in spiral mode the aircraft actually goes through changes in the roll angle as well. We can retain this variable if we want to make a 2 degree of freedom approximation, but in the textbook example it is deriving a 1 degree of freedom approximation of the spiral mode. So anyway, we drop delta P and we drop delta phi. We also drop the side force equations, so that all the y stability derivatives are dropped. So now we are down to just these two equations to approximate the spiral mode. So from here, we merge these two equations simply through substitution, and then we get a 1 degree of freedom approximation for spiral mode. We can compute the characteristic equation, and then we can see that the eigenvalue is influenced by the stability derivatives. Now let's analyze this eigenvalue equation. We know that spiral mode can be stable or unstable. So depending on the values of these stability derivatives, the eigenvalue would be positive or negative. If we want a stable spiral mode, we want the eigenvalue to be negative. So this means that this equation should ideally be less than 0. Note that in here, the L beta stability derivatives, which is the lateral stability derivative, is usually a negative value for statically stable aircraft. You can recall this from the condition for rolling static stability, that we want the CL beta to be less than 0. So the same thing applies here. So the L beta stability derivative must be less than 0. The L beta is also called the dihedral effect. So note that also the NR stability derivative, which is also called the yaw rate damping, is also usually negative. So this essentially means that the term here is already a negative value, given that this term is greater than this term. So in this inequality, we are familiar with two of the variables, the L beta, which is the rolling or lateral stability, rolling or lateral stability derivative, and the other one is the N beta, which is the yawing or directional stability derivative. So this relationship shows that a high degree of lateral stability tend to make spiral mode stable, and in contrast, a high degree of directional stability tend to make spiral unstable. Now, for the rolling mode approximation, we know that roll mode is a single degree of freedom motion, and the dynamic equation of the rolling mode is exactly the same as the pure rolling motion dynamics that we have derived in the first part of the lecture. We also know that the roll damping variable here affects the roll mode time constant, as well as it affects the steady state roll rate value. So now let's discuss the Dutch roll approximation. In Dutch roll motion, the motion is can be approximated by several ways. The actual Dutch roll motion is truly a 3-degree of freedom motion with a very strong coupling between all the motions, the yawing, the rolling, and the side slipping. But in the textbook example, it shows a method for deriving a 2-degree of freedom approximation for Dutch roll. In that sense, only 2 variables are chosen in the Dutch roll approximation. And these 2 variables are the side slip angle and the yaw rate, while the rolling moment equation is being dropped from the equation. So now the Dutch roll motion is approximated by this state space of the 2x2 state matrix. From here, we can compute the characteristic equation and then the approximate equation for Dutch roll mode frequency and the damping ratio. So the Dutch roll, it can be of a high frequency or low frequency, and it can be lightly damped or heavily damped, and the characteristics are all depends on the values of the stability derivatives in this equation. It might not be very straightforward to see from these approximate equations, but in general, a good Dutch roll motion is achieved with high directional stability. A high Cn beta term would give a better Dutch roll motion. Also, a good Dutch roll is achieved if the aircraft has low stability, low lateral stability, or low value of Cl beta, because as the value of Cl beta gets larger, then there will be more more roll coupling present during the Dutch roll, so then the motion is worse. So for a good Dutch roll, we would want the aircraft to have high directional stability but low lateral stability. But if we can go back to the Sphero approximation, we have made a remark here that for a stable spiral, we want a high lateral stability but low directional stability. And it turns out that for the Dutch roll, it's the other way around. So it is actually a trade-off between spiral stability or good Dutch roll characteristics. Usually for designing the aircraft, the spiral stability is compromised for good Dutch roll characteristics, and this is because spiral instability can usually be tolerated as long as the time to double amplitude is large, meaning it is a very slow and gradual motion. And under this condition, the pilot can return the aircraft to wings level flight easily using aileron control input.